Hi, my name is Samir Shende, and I serve as a research associate professor at the University of Oregon. And today I will describe the tau performance system. With growing hardware complexity, it is now getting harder and harder to accurately measure and optimize the performance of our HPC and AI ML workloads. The tau performance system aims to deliver a scalable, portable performance evaluation toolkit for these workloads. And more importantly, it supports the OpenCL programming model across GPUs from multiple vendors such as Intel, AMD, and NVIDIA. You can learn more about tau by visiting our webpage at tau.uoregon.edu. There are three main components of tau: the instrumentation, where you add hooks to your code; the measurement component, where we can generate profiles and traces; and the analysis component, where we can look at the performance data and visualize the data using tools such as Paraprof and Perf Explorer, and third-party trace analyzers such as Vampire, the Chrome browser, and also JumpShot, a trace analysis tool that ships with tau. Tau aims to support all the HPC platforms, compilers, and runtime systems, and aims to provide portable instrumentation, measurement, and analysis capabilities. It supports a range of languages such as C, C++, Fortran, Python, even Chapel, Java, and Spark. And it supports multiple runtime systems such as MPI, OpenSHMEM, and GPU runtime such as OpenCL, DPC++, SYCL, ROCm, CUDA, OpenACC, and thread packages such as pthread, OpenMP, using the OpenMP tools interface, and a combination of these. And it has analysis tools such as Paraprof and Perf Explorer, and also a database, the TauDB. In case you're wondering how tau can help you in your performance engineering goals, well, tau can show you where the application spends its time, at the routine level, at the outer loop level, even at the statement level, and see the time spent in OpenMP loops, in execution of OpenCL kernels running on GPUs, even the data transfer between the host and the GPU. Instead of time, you can also see hardware performance counter data from tools such as PAPI and Liquid. It can show you the memory usage. It can show you the memory footprint of the application, energy usage, IO characteristics, peak read and write bandwidth, and volume of data on a per file basis, even how the application scales, the efficiency, runtime breakdown of performance across multiple cores. To do this, you must have hooks in the code that perform the measurements. And these hooks or instrumentation can be added by a preprocessor, by a compiler, and also using the tau exec tool, which preloads tau's DSO or dynamic shared object, and then it can perform the measurements. There's no need to recompile your application when you use the tau exec tool. And it can generate profiles as well as traces, while profiles show you how much total time was spent across all invocations, the cumulative summary statistics of performance data. Tracing can show you what each thread of execution was doing at any point in time, and it shows you the events along a timeline display. Paraprof is the profile browser that ships with tau, and you can see multiple MPI ranks in this case. It can show you multiple threads of execution, and these colors represent code regions. You can separate them out by just unstacking these bars together so you can see how much time is spent in a particular code region. Here is an example of the node level data, which shows you the .tau application as the top level timer, and all the events take place within this top level timer, which can be roughly equated to the main. And this is the inclusive profile. This is the exclusive profile that shows you the time spent in loops. And here is an example of an OpenCL profile where I can see the time spent in the different kernels running on the GPU here. One of the kernels is called multiply matrices, and I launch it using tau exec with the tag such as cupd, and OpenCL is the option chosen. So we can generate detailed OpenCL statistics like these. Here is an example of using tau with Intel 1 API with DPC++ SYCL. And you can see the execution of kernels with even level 0 runtime layer profiled. Here is an example of how to do that. This is a trace file visualized in the Vampire commercial trace visualizer, which comes from TU Dresden in Germany. And here we see the Intel 1 API with OpenCL running on 4 different MPI ranks. And we are able to generate the data using the tau trace flag set to 1. And if tau is configured with OTF options, you can set the tau trace format to OTF2 and launch the execution using MPI and tau exec with the OpenCL. This is the trace visualizer that ships with tau, jump shot, which shows you boxes within boxes to show levels of nesting. And you can also see the Chrome browser, or you can go to perfecto.dev and load a JSON file that can be generated like this by running the application, then merging the traces, and then converting them into a JSON format and loading the trace file, where we can see a flame graph from each rank, and you can see the levels of nesting vertically in a flame graph. This is the 3D profile browser that comes with Paraprof. And here you can see the threads of execution. You can see the code regions and the time spent in the different code regions along the height and color axis. Where these two crosshairs intersect for the function and thread, you can see the height and color value in detail. And this is the communication window, the 3D communication display, which shows you the extent of communication between sender and receiver ranks. You can simply launch an application with the event-based sampling flag or the tau exec-EBS flag, and an uninstrumented application can reveal details about the function where the samples were taken, the file, the line number, and how much time is spent across all of the ranks. And this is the same display with jump shot and Chrome. And this is the Vampire trace visualizer from TU Dresden, where we can see details coming from Cocos, the node level parallelism package, which can show you the time spent in different Cocos kernels along a timeline view in Vampire using tau. So tau has support for many different runtime systems. As you saw, we have support for MPI, pthread, OpenMP, OpenACC, and also OpenCL, where we can track fine-grained kernel execution on the GPUs. We have support for the CUDA profiling tools interface with CUDA, level 0 with DPC++ SYCL, and Intel 1 API, and ROCm from AMD, Cocos, and Python, to name a few. And you can just mix and match these interfaces. So you can see that the execution with level 0 with MPI or MPI with OpenCL, and enable the different configurations of tau. Now, if I wanted to support tau for OpenCL on 3 different GPUs, then I can just download tau, untar it, go to the tau directory, and just configure it with this BFD equals download. This is a very important flag. It allows us to use the GNU binutils package to translate the address to the source line location. And then you can choose CUDA. You can even provide an optional tag. Like I'm saying, CUDA is in this directory, but use the tag of NVIDIA. And then it will create a makefile.tau NVIDIA cupd. I can specify BFD equals download with the OpenCL for the Intel tag, and it will create this stub makefile. And then I can create this with OpenCL with ROCm 510, and it will, with the tag of AMD, create this stub makefile, which then keeps track of all the directories and compilers in these makefiles. Now you can go to a directory and just say tau exec-t serial, and then if it's not MPI application, then you have to say serial. Then specify these tags that we just used, one of these, and then dash OpenCL to run the application. And then you can launch the pprof tool, which is a text browser for performance data, and paraprof, which is a GUI. So tau exec is the tool that will intercept the runtime calls for OpenCL, and you don't need to modify the executable binary. That's right. There's no change to the source code. There's no change to the build system. There's no change to the binary. You just launch it with tau exec, and it preloads the wrapper interposition library that intercepts the calls. And then you can enable other options such as event-based sampling or EBS, the communication matrix display, generating OTF2 traces, etc. And this is how it looks. If you're running an application without any instrumentation in this way, then you can just change that to launch it with tau exec with the kubectl or OpenCL or ROCm or OpenACC or other options. So here is the example with IO profiling, event-based sampling, OpenMP tools interface. And you can set these runtime environment variables to get details. For example, you can set the tau trace variable to generate trace files, or com matrix to generate a communication matrix, or set the tau metrics to be time with some PAPI hardware performance counter data. The preset values or the native values can be specified like this. Here are some additional environment variables that tau supports. And I would like to thank our sponsors, the Department of Energy, Department of Defense, the National Science Foundation, NASA, CEA in France, our industry partners, AMD, ARM, Intel, NVIDIA, IBM, and our partners at other universities and institutions, including University of Oregon, the Ohio State University, Paratools, the University of Tennessee, Knoxville, TU Dresden in Germany, and Jülich Supercomputing Center. I would like to thank the Exascale Computing Project for sponsoring this work in the tau performance system. And I'll show you a demo of how to use tau on 3 different GPU architectures. So let's start with, say, an NVIDIA GPU. Here is a machine with A100 GPU, and I have just downloaded tau. I can say which NVCC, and it's in my path. So I can configure tau, as I showed before, with the BFD equals download, and give the CUDA directory, which is this, where OpenCL is located. And then just give a tag such as NVIDIA. And then say make install -j. Now it will configure tau. It will find the OpenCL libraries. It will build tau, and I'll be able to generate performance data with this build. If I want to look at another GPU architecture, it built this makefile.tau NVIDIA kubectl because I specified the NVIDIA tag. Here is an Intel GPU, and I can say CL info, and I can see that it has a DG1 GPU. I can say configure -OpenCL with the BFD equals download, and maybe put a tag of, say, Intel, and make install -j. And this will generate the tau library for OpenCL profiling, and it will have a name which will have a tag of Intel. And then maybe I can target the AMD GPUs with support for OpenCL. And to do that, it's completing the install. It takes less than a minute sometimes to just install the library. And there it is. It made a tau with the Intel tag. So we can distinguish this from the tau with the NVIDIA with CUPTI. And let me go to the same directory and go to this system, which has two AMD GPUs. And these GPUs are the GFX 908. So there are two of these GPUs that we have here on this machine. So here I can see opt ROCm 510 OpenCL directory exists. So I can say BFDs download OpenCL equals opt ROCm 510 OpenCL and give a tag of AMD. With this, we'll have installed tau for 3 different GPU architectures in the same directory, but with 3 different tags. So let me build an example and try a simple matrix multiply example and generate the performance data with that. And here is an examples. Yeah, clean. So all I have is this matmult.cpp, and you can see it's has a matrix size of 8192, and this is the OpenCL program. So how do I compile this? I say make, and it uses the OpenCL ROCm 510 directory. It links in the OpenCL library. I can say matmult, and here is the OpenCL library from AMD. And if I run the program normally like this, then after putting tau in my path, I'll have tau exec, and I can say tau exec -t serial, because it's not an MPI program, AMD with the -OpenCL with the matmult. And this will run the same program, but it will generate the data from tau. And you can see this is for the host, this is for this GPU 1, and this is GPU 2. I can look at the data using pprof like this, and I can launch paraprof, the GUI tool, and I can see the execution of this multiply matrices on 2 different nodes. It took roughly the same time. And here is the time spent in the OpenCL calls. You can see exactly how much time was spent in which OpenCL call. You can also have a 3D browser, and you can see the functions and various metrics. And you can see the create this function. create buffer. There are 3 threads of execution. So that is something that I just did on the AMD GPU. If I go to CL, OpenCL, NVIDIA, and this is the same program. I can say make LDD matmult, and it's using the CUDA's OpenCL. If I say I run it like this on the A100 GPU, then I could say tau exec -t serial with NVIDIA with OpenCL, and then I can give the matmult, and it will run this on the A100 GPU. I'll be able to launch paraprof and see the timings. Here is the time spent in OpenCL calls. Here is the time spent in the GPU execution with multiply matrices. You can see the metadata for the thread that it captures, which shows you all the options. And then here, let me just try another example with Intel GPUs. This time, let me just go to examples, samples. Create a build directory. I'll do a CMake, and it finds make. I can say CLgen GPU, say 4096, and it will run this on the Iris Xe Max Intel GPU. And if I want to profile this, I can say tau exec -t serial Intel -OpenCL, then CLgen GPU 4096. And then it runs this, and I can see it takes this time to launch paraprof and visualize the results. Here is the gem kernel, which executes 4 times, and you can see that there are 4 calls to the gem over here, and then you can see the time spent in the OpenCL call like this. So we just showed you how to use tau, how to build it, how to run it with OpenCL programs across 3 different GPU architectures. I hope you find this useful and you can use this tool in your workflow. Thank you.